remember what a net is? A net is a mapping from a directed system into another set. And it will turn out that integrals are mappings of directed systems. Here we partition AB, and for every partition, when we form a Cauchy sum or Riemann sum, we get some real number out. So what we will be doing is the directed system of partitions will be mapped into real numbers, and it will be a net. And a net converges just like a sequence. So whenever the net converges, that's an integral. That's a very sophisticated way of looking at integration. You have a convergent net where the domain is the set of partitions on a given interval, and of course you're mapping to the real numbers. So we'll do that in specific examples, but I just wanted you to see that this is the modern way of doing it. Okay? Nets are generalized sequences. A sequence, you can only have a countable number of points in the sequence. With a net, you can have any number. Very uncountable if necessary. And of course, just stop and think, how many partitions of the interval AB, if it's a proper interval, in other words, B is greater than A. How many partitions are there? What's the cardinality of the number of partitions possible? Well, you have Aleph-1 choices for the left endpoint, and Aleph-1 choices for the right endpoint. And we know enough transfinite arithmetic that Aleph-1 times Aleph-1 is Aleph-1. I love that. Okay. What's Aleph-0 times Aleph? One. What's Aleph-alpha times Aleph-beta? Yes, sir. What's Aleph-alpha plus Aleph-beta? Same thing. Absolutely. So you remember. Okay. So the point is, there's a damn lot of partitions. That's why you need a net. Sequences won't do because you have way beyond countably many partitions, right? Okay. All right. So. Okay, so there you go. If a partition gets finer and finer, it pulls the norm with it. But in some situations, phrasing the definition of integral in terms of defined partitions rather than norms gives you some theoretical advantages. You can work with the definitions more easily. You can prove theorems more easily. It's easier to handle the partitions themselves than the norm of the partition. Okay? I made that point again there about the definition of derivative. Same thing. If you pick the right definition, here's the game. You have a basic definition, and it's awkward. So you have another definition that's equivalent to it. The one implies the other. But this one's easier to apply in practice. You can prove stuff easier, faster, better, more transparently with the other definition. That's why somebody is motivated to develop, right? It's a really good basic definition. You just go on. But some of these subtle definitions, you can improve them. Darboh did that with the Riemann. So we'll study that in a second. All right. Now, this business about picking a point inside a subinterval so that one can actually construct an elementary rectangle. What do you need? You need the base of the rectangle and you need the height. Well, the base is going to be the width of the subinterval. What do you pick for the height? You have to go find the function and evaluate it at some point in the subinterval, right? A point in the subinterval is a tag for that subinterval. If you have a complete set of tags, that means you have one point selected from each subinterval. So the set of tags goes with a particular partition. You just can't have a set of tags out there in space. It has to be coordinated with the selection of the partition points. When you take the pair, the partition, and the set of tags together, you have a tagged partition. The partition can exist without the tags. It's just a chopping of a baby. But now, if I select somebody in each subinterval, and I make that list, and also give you the list of the partition points, those two sets together constitute a tagged partition. Okay? All right. All right, now, definition of the Cauchy integral. Functions defined on AB, and if that limit exists, then we say that the Cauchy integral of f exists on AB and equals that limit. Notice with that C in the front, what's that limit really mean? We say the limit is the partition 1 goes to 0 of that sum. If it exists, that is the Cauchy integral. But what's it mean for that limit to exist? Well, like all limits, real numbers, we go pick an epsilon greater than 0. And then we have to find a delta that in general depends on that epsilon, and certainly on the function that we're trying to form the integral. So that whenever the norm of a partition of that integral AB is no bigger than the delta, it means that the difference between the sum constructed that way and the limit is less than epsilon. You'll notice the point in there, f of x sub I minus 1. That's the feature, the defining feature of the Cauchy integral. It's the left endpoint of the subinterval. It's a tagged point, but it's the set of tags is the set of tags is the set of partition points. You use the left partition point each time, right? That's why it's not just some random point in the middle of that interval. It's always the left point. You can do the same thing on the right if you want. Form another Cauchy prime integral, I guess. But that's what it means for this limit to exist. The partition going to 0 means you pick an epsilon, and then for every partition that has norm no greater than the associated delta, the difference between that Cauchy sum and the limit is less than epsilon, in which case you say that the Cauchy integral of f of x on AB is the limit L. Okay? We have sorted that out. That's the basic idea. Those, graphically, what is that? Graphically, what's that look like? If we're doing a Cauchy integral, with the functions tooling along here, and say we're going from A to B, and we have a nice partition here. Notice the partition rectangles don't all have to be the same width. So this is x naught, x1, x2, x3, etc. So what I do is take this width and this value of the function to get an elementary rectangle that looks like that. And then this one, right? And then that one, and then these are going to be shy on this end. These are kind of over there. So this is a plus error, hardly any error there. These are all minus errors, right? But as we force the norm of the partition down, these things get closer and closer together, and the error, this little excess area here and deficit area here, those things go away. Hopefully, if it's a function that we can integrate, every continuous function is Cauchy integrable. Another way to say that is it's integrable in the Cauchy sense. So the Cauchy integral of this thing looks like, yeah, no problem. Now, here's the thing they do in calculus course to explain the integral. If you combine the Cauchy idea with the following idea that's often presented in calculus books, you can have a horrible mistake.